Okay, hello everyone. Myself Surendra Srinivas. So today we are kicking off a new series on semiconductor physics. So in this video we will be revisiting some of the fundamental formulas and concepts in semiconductor physics which are considered as the core principles that form the building blocks for solving the textbook questions. In the upcoming videos we'll use these formulas to solve some of the common textbook problems. So basically, we'll be using this textbook called Fundamentals of Microelectronics by Behzad Razavi. So yeah, let's gain some deeper understanding of the subject and let us improve our problem solving skills. So make sure to stay tuned and follow along with the series. Now let's just jump right in with the essentials. Okay, so the story starts with this equation, that is Ni equals to 5.2 into 10 power 15 times t power 3 by 2 exponential of minus Eg by 2 kt. This is the number of electrons per cubic meter. This is for silicon. What does this equation give? This equation tells us the number of electrons per cubic meter. Why are we not interested in full number of electrons in the substrate? Why only these? Because free electrons constitute current. Unlike a conductor, the free electrons in silicon are restricted with temperature. Silicon has this interesting property that at absolute zero, there are no free electrons. But in room temperature, the electrons gain some energy, break the covalent bond, and jump into conduction band, making themselves as free electrons. So those total number of free electrons per cubic meter is given by this equation. Okay, now let us dig the equation. The Eg is known as band gap energy, that is 1.12 electron volt for silicon, and K is the Boltzmann constant whose value is 1.38 into 10 power minus 23 joule per Kelvin. Okay, now 1 electron volt is 1.6 into 10 power minus 19 joule. Yeah, this is done. And we have for intrinsic semiconductor, number of electrons equals to number of holes, that is equals to number of free electrons. Sorry, concentration of electrons equals to concentration of holes equals to concentration of the charge carriers in intrinsic state squared. But for extrinsic semiconductor, this equals to doesn't hold true, but the product does. Okay, sorry. NP equals to Ni square. This equals to doesn't hold true, but the product does. Now, for drift current, we can write the equation as minus V WH considering the current is the flow of positive charge carriers. So bringing WH the radius of the cross section to the left side, we get current density as VNQ. Now V is mu times E. As we know, the drift velocity is directly proportional to the electric field. For electron, it is negative. So J will be mu ENQ, where mu is the mobility of the charge carrier. For electron, it's 1350 centimeter square per volt second. For holes, it is 480 centimeter square per volt second. Okay, now let's talk about diffusion current. Diffusion current is a result of changing concentration of the opposite charge carriers. So the current depends upon the gradient of the concentration of the charge carrier and also depends upon the area of the cross section of the substrate and charge of the charge carrier. Okay, now removing this proportionality, we get I by A is J, that is equals to dq dn by dx, where d is the diffusion constant of the charge carrier. For electron, that is 34 centimeter per second. For hole, that is 12 centimeter per second. Okay, we can also write J total as dn by dx minus dp by dx into q. This is diffusion. For drift we can write as J equals to mu p uh, mu p into mu p into np plus mu n into nm into eq. Okay, what do we have next? Next we have Einstein relation. Einstein relation is given by diffusion constant of the charge carrier. The ratio of diffusion constant of the charge carrier to its mobility is equals to kT by q, that is equals to 26 millivolt for T is equals to 300 Kelvin. Okay, then we have barrier potential. Basically barrier potential forms whenever the p-n junction diode is in equilibrium. So the current due to drift is exactly equal to the current due to diffusion. Okay, QWHVN equals to AQ dm by dx. So this can be more simplified as mu e p, AQ cancelled, V is mu e. Consider this as a whole concentration. We get dp by dx. Okay, now we have mu by dp. E is written as minus dv by dx, so it's minus dv, dx will be cancelled. That is equals to dp by p. If we integrate on both sides from x1 to x2, from pn to pp, we get v of x2 minus v of x1 is equals to minus dp by mu p ln pp by pn. Okay, we can also write this as mod v naught is equals to dp by mu p is Einstein relation, let's say that's threshold voltage, or kT by q into ln na nd by na square. This is your homework. Tell me in the comments how is this derived from here. The hint is use this relation, the product npn is equal to n square. Okay, what do you have next? Next we have junction capacitance. So basically the junction capacitance is defined as the capacitance formed due to the charge accumulated at the depletion region. It just basically acts as a variable capacitor with variable reverse bias voltage. We'll see that how. The capacitance is given as Cj equals to Cj naught by 1 minus Vr by V naught, where Vr is the reverse bias voltage. If it reduces, Cj will obviously be reduces. Okay, where Cj naught is equals to epsilon silicon Q by 2 into Na Nd by Na plus Nd into 1 by V naught, where epsilon silicon is the dielectric constant of the silicon is equals to 11.7 epsilon naught, where epsilon is the dielectric constant of vacuum and 11.7 is the dielectric constant. It's a basically relative dielectric constant relative to vacuum for silicon. So relative dielectric constant is 11.7 and dielectric constant for vacuum is 8.85 into 10 power minus 14 farad per centimeter. Okay. Yeah, and V naught will be our barrier potential, this equation. Next we have okay, next let's talk about forward bias current. Okay, so basically this forward bias current is a result of the current due to external voltage supply, uh, positive voltage supply to the diode, and that is due to change in concentrations from equilibrium to forward biased. So in equilibrium, condition, the number of electrons will be pp during equilibrium by exponential of v naught by vt. For p and f, during forward bias, we have net voltage will be reduced v naught minus vf by vt. This change in concentration gives the forward current. Let's not see the derivation completely. I'm just giving you an idea. Current will be is into exponential of vf by vt minus 1, where is reverse saturation current, whose equation is aq ni square into dp by na lp plus dn by nd ln, where d is the diffusion constant of the charge carrier, l is the length of diffusion. These two are very important equations we will be using in the upcoming videos. And to give more idea context on this, delta pn is equals to, we can write this as this will be na by exponential of, if you take v naught by vt and if you separate this vf by vt, we get exponential of vf by vt minus 1. This is for electron majority charge carriers. If you write similarly for magnetic charge carriers, you get nd. So basically current will be directly proportional to na plus nd by exponential of v naught by vt times exponential of vf by vt minus 1. So this is how these equations are derived. So yeah, I think we have covered all of the basic fundamentals. Yeah, so all right, so these are the basic fundamentals you'll be needing for understanding semiconductor physics. Remember, these fundamentals are the backbone of solving more complex problems, so it's worth spending time with them. Okay, in the upcoming videos we'll start applying these concepts to actual textbook problems, breaking down each step to make sure you can follow along and tackle similar problems on your own. So yeah, thanks for watching. Bye, we'll meet you in the next video.